Alright, in this lesson, which is lesson 11, Applying Newton's Laws, we're going to go over different problems in increasing difficulty, but we're going to use a systematic way in doing it. And it's going to be the same way we do every forces problem in this entire course. Okay, and I have the steps for you on this page, these 8 steps. They're also in your textbook. I took these right from your textbook, okay, on page 88. Steps 1 to 8, and we're going to go over these 4 steps as we solve the next 4 problems on the back of this sheet. Okay. Next slide. So the problems, we're going to start with objects on a flat surface, and then we're going to incline the surface, and then we're going to add pulleys, okay? And then we're going to have a combination of pulleys with inclined surface, and to have multiple blocks, more than just one, right? Have 2, 3 blocks, okay? And then tomorrow we'll even add friction to it. Okay, it sounds like it gets really complicated, but again, the strategies you use to solve the simplest question will be the same strategies used to solve the hardest question. All right, so let's start with the first question. So you know what? I'm going to leave these up on the screen. So the first question says a 10-kilogram box is being pulled by a string attached to it at an angle of 30 degrees to the horizontal across a frictionless surface. If the applied force is 40 newtons, calculate A, the acceleration of the box. See, can I make this bigger? No. All right. So step 1 says read the problem carefully. Okay, we did that, but if you need to read it again, if there's even one word in there you don't quite understand, it can change the question. So read through it very carefully. Then draw a diagram. Not necessarily a free body diagram, but a diagram of everything that's happening. So do this. We have a 10-kilogram box, so put our 10-kilogram box, and we're just going to write information on the diagram as well. Being pulled by a string attached to an angle of 30 degrees. Let's put this string, let's call this a tension force at an angle of 30 degrees. And if the applied force is 40 newtons, that's our tension force. I just wrote tension because it's a rope. 40 newtons. Calculate the acceleration of the box. Okay, so there's our diagram. It looks like a free body diagram, and it kind of is. A system diagram, you'll add more things going on for more complicated problems. But the next step is number 3, draw a free body diagram. And there actually is more forces here. We have gravity, and we have the normal force. Now when you draw a free body diagram, and this says here, label all the forces and choose your positive x and positive y components. I want you to always write down a coordinate system. So let's choose positive x here and positive y here. Now I'm going to give you a hint, and this is a very, very important hint. Let me make this bigger. Okay. Choosing the right coordinate system can make a question a lot easier. Choosing the wrong coordinate system, well, there is no wrong coordinate system, but there are coordinate systems that you can choose that make the problem unnecessarily difficult. And here's the hint I'm going to give you. Okay, you can even write it down. You're going to always choose your positive direction. Positive, that's how I write positive plus VE. Positive direction in the same direction as acceleration. Okay, because we are going to be using Newton's second law, F equals ma. Okay, and sometimes if you choose your positive direction, in this case acceleration is in that direction. So if I were to choose positive x in that direction, I get a lot of students, well, they would write a component of tension to be negative, but then they would leave acceleration as positive. Students tend to forget in this equation, acceleration is also a vector. It's going to have components depending on what you choose your coordinate system to be. If I were to rotate the coordinate system like this, well, acceleration is in this direction. So that means acceleration is going to have to be broken up into these components. Why would I make my life difficult by doing that? I don't know. You could, and you could still get the right answer. It'll be a lot more work, but you could do it. Also, if I made this positive, then acceleration must be negative. Okay, so just to avoid having to deal with possible components for accelerations or possible negative accelerations, just to keep things a little bit more simpler, we're going to always choose our positive direction, whether it be x or y, your choice, to be the direction of acceleration. So that's x in this case. And y is always going to be perpendicular to that because this is a Cartesian coordinate system. Now, since it's not accelerating up or down, it doesn't really matter which direction you choose to be positive. So I'm just going to go with up as being positive. All right. Now let's continue. What was the next step in our systematic approach? Calculate components. So in this case, we have components. Make this big again. In this case, we have components, right? Our tension or applied force, whatever you want to call it, is not aligned with our coordinate system. So we have to draw components. So here's our components. You don't need to actually calculate with a calculator yet. In fact, just write down an expression. So in this case, our x component would be 40 cos 30. And our y component would be 40 sine 30. All right, so we've handled calculating the components. And what's our next step? Write down Newton's second law. So we're going to write down Newton's second law, and we're going to write it down for both x and y. Okay, and then if you need to, repeat these steps over and over again. If you have multiple objects, multiple free body diagrams, just repeat these steps. We will have multiple objects. If you have 2 objects, I'm probably going to make you solve 2 equations for 2 unknowns. 3 objects, 3 equations for 3 unknowns, right? Even 2 objects where one of them is on a ramp, right? Lots of different possibilities, and we're going to go over those examples. So let me just make this big again. Okay, so we need to get back to solving the problem. It's asking us to find the acceleration of the box. So we have our 2 equations. Now in these equations we have ax and ay. But in our case, the box is accelerating horizontally. So ax is the value of acceleration because there is no y component of acceleration. Ay is 0. Okay, so here's what our 2 equations have reduced to. Now, since we're actually trying to solve for acceleration, I'm going to look at this equation. So how many components do we actually have in x? So if we're to sum up all of our forces in x, okay, how many forces in x do we have? Well, in this case, we only have this one here. Okay, so I'll just write down 40 cos 30 equals ma, and the mass is 10. So let's write 10a. Now you can just solve for a. Divide both sides by 10. 40 over 10 is just 4, so you get acceleration equals 4 times the cos of 30. Now is when you can take out your calculator. Make sure it's in degrees, not radians. Do 4 times the cos of 30. It's 3.4641, so we got lots. But how many significant digits do we need? Looks like in the question 3. Okay, so 3.46. Okay, and we can just label that forward because acceleration is a vector there. Now part B says the magnitude of the normal force. All right, let me just erase part A. Now part B, we're actually going to use the next equation. Since we're actually trying to figure out what the normal force is in our y component, so why not use our y equation? Now I forgot, I erased FG here. Now what I get a lot of times is students say, oh, normal force, that's just equal to gravity. No, it can be, right? If I just take this object, right, and rest it on my hand, okay, it's got a force of gravity acting down and a normal force acting up. It's not accelerating, and those are the only two forces acting on it. Therefore, it's in equilibrium, and yes, normal force must be equal and opposite to gravity. But what if I put this calculator on top of it? Now let's just look at the eraser here. The eraser now has gravity pushing down on it of the eraser, and the force of gravity of the calculator is pushing down on it. And then there's a normal force pushing up. So in this case, is the force of gravity acting on the eraser the same as the normal force? No, in this case, it's the total force of gravity, which is equal to the normal force. Similarly, I could have an applied force. I can push down on the eraser. Now, if I drew that as a free body diagram, we have gravity pushing down on the eraser. We have me pushing down on the eraser. And we have the normal force acting up. Does normal force equal to gravity? Well, if that were true and the normal force equals to gravity, they would cancel, and we're left with a net force of my applied force, and therefore it should be accelerating down, but it's not. So that doesn't make sense. So in this case, since it's an equilibrium, I think it's safe to say that the sum of those two forces are equal to the normal force, at least the magnitude anyways. And this is very similar to the problem we have right here. In this problem, how many forces do we have acting in y? Well, we have gravity and normal, but then we're also slightly lifting up the eraser because we have a tension or applied force, which is vertical. Now, it's not enough to overcome gravity, so the eraser isn't actually lifting upwards. It's still on the surface. But with that applied force, does the normal still equal gravity? Let's actually try using the equation to prove it. So I'm going to rewrite this equation over here. So the sum of all forces in y equals 0. Now what forces do we have in y? Well, I just circled them. 1, 2, and 3. And since I've labeled up to be positive, let's have the normal force plus this component of tension, 40 sine 30, and then minus gravity, which we know is mg, equals 0. Now, if I were to solve for the normal force, I don't get the normal force equaling to mg. I get the normal force equaling to mg minus 40 sine 30. Okay. Now the mass is 10 kilograms, so we'll have 10 times 9.81 minus 40 sine 30. And this is where we can get our calculators out. Minus 40 times the sine of 30. 78.1 newtons. Okay, so that's question 1. And that's probably similar to a question you've done in grade 11. So let's move on to question 2. And again, you're going to see that we're going to apply the same strategies. We're going to read the question carefully. We're going to draw a diagram of what's happening. We're going to draw free body diagrams, a coordinate system, components, and then apply Newton's laws. Every time, every question, same steps. So question 2. Question 2 says, a box of mass m is sliding down a frictionless surface that is inclined at an angle theta. Find an expression for the acceleration of the box. Okay. I usually get a lot of students freaking out with this question saying, where's all the numbers? There's no numbers. There's not a single number in this question. It's true, but the question doesn't ask you for a number either, does it? It asks you for an expression. And a lot of questions are like this as you move forward, as you continue to go forward into physics, right? Most of the time we don't care about one specific number, right? That doesn't really tell us the big picture, right? For example, if I just told you 10 newtons, what does that mean, right? Is it weight? Is it an applied force? Like, what's happening here? But if I said applied force equals, I don't know, tension minus some frictional force, that tells you so much more than 10 newtons. It tells us that some applied force is equal to, there's obviously some kind of tension acting on an object, and it's moving because we have kinetic friction there as well. So it tells you so much more. Not only that, it tells us that the applied force is, well, causing something to move, right? Because if the applied force was 0, well then what would happen? In that case, it looks like if you rearrange, tension would be equal to kinetic friction, in which case there would be no more acceleration. Now, it could still be moving, right? Because there is still kinetic friction. And if kinetic friction was gone, tension equals 0, right? But again, it could still be moving. Remember that a net force of 0 does not mean an object is at rest. It just means its motion's not being changed. But there's so much more you can learn from an expression than a simple value. So in this case, we're going to see what we can learn from these expressions. We have a ramp. Right? We have an object on a ramp with some mass m. And the ramp's at some angle theta. Find an expression for the acceleration of the box. Okay, now, before we do this, I have a question for you. We've learned in grade 11, if you take an object and you drop it, right? If there's no air resistance, it accelerates down at 9.81 meters per second squared on the Earth. And it doesn't matter what the mass of that object is. What about if we let an object slide down a ramp? There's no friction, and again, no air resistance. Does it matter what the mass of that object is? Will it accelerate at the same rate? Yes or no? Okay, so think about it, because solving this question without numbers is going to tell us that answer. All right, but before we do that, this is really an incomplete diagram. We need to follow the steps that we went through before. Let's draw the forces that are acting on this. So we have gravity. Gravity is straight down, mg. We have the normal force, which is always perpendicular to the surface. And that's it. We don't have an applied force. Just because something is not moving, just because something is moving doesn't mean there has to be an applied force on it, right? This falling doesn't have an applied force on it, but it's still falling. Okay. What's next? What are we missing here? Well, we don't have a coordinate system, so let's choose a coordinate system. And let's choose it based on the hint I gave you. We need to choose the positive direction of one of our axes to be in the same direction of acceleration. So what direction is this accelerating in? It's actually accelerating down the ramp. So let's choose down the ramp to be our positive x-axis. And of course, the y-axis, which is perpendicular to that, we'll just choose in that direction to be positive. Okay, that's done. Now we need to find any vectors that's not aligned with either of those axes and draw components for. Normal force is perfectly aligned with our y-axis, but gravity is not. So we need to draw components. We need to draw a y component and an x component. So let's start with our y component right there. And our x component, which is parallel to the ramp. Okay, our vector is down, so it's going to be the addition of our y and x vectors. And this is, of course, 90 degrees because our x and y axes are always perpendicular to each other. But here's the question. One of these two angles is equal to theta. Do you know which one it is? Think about it. And you can think about it in terms of what would happen if the ramp's very small or very large. Or you can do some trigonometry and work with it. Okay, pause the video. I want you to try and figure this out before I continue. Okay, now I'm going to assume you've unpaused the video. So let's look at this two different ways. One, what if the ramp had an angle very, very small, like a couple degrees, like this? Let me redraw this. This vector is down, and so it looks like this. Now, this is a very small angle. Which one of these two angles is also very small? It's the top one, isn't it? Now what if I drew an angle that's very big, like a ramp like that? Here's gravity, and here would be our y component and our x component. Okay, now which of these angles is very large, like this one? It's the top one, right? Okay, so looks like the top one's theta. That's one way of looking at it, looking at the extremes to see how that fits. Another way of looking at it is just doing some trigonometry. Where's my PowerPoint? I'm just going to fast forward to the question we're on. These PowerPoints are all online, by the way, so you should be able to look at them if you need to. Okay. So getting back to this, doing some trigonometry. Now right here, gravity is straight down. And since this is straight across, we know that's 90 degrees. Therefore, this angle, just using the fact that all angles add up to 180 in a triangle, that would be 90 minus theta. Okay, now this one, right, is parallel to normal force, and because it's along our y-axis, right, and this is parallel to our x-axis because that's how we chose. So that would be 90 degrees right there. And therefore, this angle here would be 90 minus 90 minus theta, which just leaves us with theta. So that's our angle theta. I'm just going to get rid of this. Now the next step was to write components. Right? So here is, we can't calculate them, but I told you we don't need to calculate them. We're just going to write an expression for them. So this one would be mg times the cos of theta, and this one is mg times the sine of theta. All right, looks like we have everything. The next step is to apply Newton's second law. Since we're solving for acceleration, let's do it along the x-axis. So the sum of all forces in x equals m times ax, where ax is just equal to a. All right, so how many forces do we have actually acting in x? If you look at them all, we just have one, mg sine theta. So let's write this as mg sine theta equals ma. And then, here's our answer to the question I posed at the very beginning. Mass cancels. And you simply get acceleration equal to g sine theta. Now, another thing that's always good when you're doing physics is looking at the answer and asking yourself, does that make sense? So let's look at this. Does this make sense? Well, let's look at it in two situations. We're going to do the extremes again. Let's say theta was very, very small, actually 0. So bring theta down to 0 and you have a block just sitting on a horizontal surface. Right? Well, what's the sign of 0? Sign of 0 is just 0. 0 times g is 0, and so acceleration is 0. Does that make sense? You have a block just sitting there on a horizontal surface? Yeah, that makes sense. What if we took this angle and made it 90 degrees? And so the block just falls. Well, it should fall just at 9.81 meters per second squared, or g. Well, let's look at our equation. Sine of 90 is what? 1. And so a just equals g. So this makes actually great sense, and it tells you a lot about what's happening here. Not only does it tell us our extreme situations, the range at which the acceleration is going to occur from 0 to 9.81 meters per second squared, but it also told us that mass does not matter. Any object falling down a ramp in this situation, right, with no air resistance, no friction, will slide down that ramp at the same rate regardless of the mass of the object. Okay. Now the next question says, part B, what's the magnitude of the normal force? Okay. Well, the normal force is in our y component, so let's redo this for the y component. Sum of all forces in y equals, in this case, it's going to be 0. Now, a lot of students always freak out by that. So how is it possibly 0? It's sliding down the ramp. There must be some vertical component. But be careful. There is a vertical component, but is our y-axis that we've chosen in our coordinate system completely vertical? It's not, is it? Right? Our y-axis is not vertical. It's perpendicular to the ramp. So my question is, does this block ever move perpendicular to the ramp it's sliding on? No, it doesn't. So the sum of all forces in our y-axis is 0. Now, how many forces do we have in our y-axis? Well, we have this component of gravity and our normal force. And we chose the normal force to be positive, so we'll have Fn minus mg cos theta, which equals 0. And if we solve for Fn, we just get mg cos theta. So does that make sense? Again, let's look at our extremes. If this was a flat surface and theta was 0, cos of 0 is 1, the normal force equals mg. That makes sense. An object just sitting on a surface, right? The normal force is equal to the force of gravity. What if I remove that surface by making this 90 degrees? What's the normal force? It should be 0 because it's no longer in contact with anything. Well, what's the cos of 90? 0. And so the normal force is 0. This makes perfect sense. All right, let's start making things more challenging and moving on to question 3. Question 3 says, and this is actually still a grade 11 problem, but it's going to really help us lead into question 4, which is more of a grade 12 problem, at least an introduction to one. Question 3 says we have two blocks of masses 4 kilograms and 3 kilograms are placed in contact with each other on a smooth horizontal surface as shown below. A constant horizontal force of 9 newtons is applied to the 4 kilogram mass. Find the acceleration and the contact force between them. So read the question and then draw a system diagram. Now this is going to make perfect sense when I say draw a system diagram because I am going to be drawing more than one object. Here's our first one, which is 4 kilograms, and that's in contact with a smaller one, which is 3 kilograms. All right, so you have 4 kilograms and 3 kilograms. And there's a contact force in between them. We also are being pushed at 9 newtons applied. So you have 9 newtons pushing on the 4 kilogram block. Now, that's definitely not a free body diagram because you wouldn't write a force going into an object, right? Your vector should always be pointing outwards from your free body diagram. So this is a good system diagram. Then it says, where's the question? Find the magnitude of the acceleration. Okay. So here's what we're going to do. Now, to find the magnitude of the acceleration, we need a free body diagram. And we have a couple choices here. We can choose to make a free body diagram of the 4 kilogram block. We can draw a free body diagram for the 3 kilogram block. There's also one more choice. We can draw a free body diagram of the system. And imagine, since they're in contact and moving together, imagine they're one object. And draw a free body diagram for this 4 plus 3, 7 kilogram object. Okay. Now, to find acceleration, it's always easiest to think of it as a system and solve the 7 kilogram block. Why? Well, what forces are acting on this? We have our applied force of 9 newtons, and then we have gravity and normal. No friction yet. And I'm going to erase our system diagram. Okay, and of course we need a coordinate system. Since it's accelerating in that direction, let's choose that to be our positive x direction. All right. Next, do we need to draw components for any of those? No. Next, Newton's second law. Since I'm solving for acceleration, I'm going to apply Newton's second law in our x direction. So net force in x equals mass times acceleration in x, but ax equals a. And how many forces do we have in x? Just the one. It's 9 newtons. The mass is 7 kilograms times a. Fairly simple, quick question, right? A equals 9 divided by 7, which is 2.3. No, 2.3. 1.3? It's late. My mind's not working. 1.3. There we go. And that's it for part A. Now part B says the contact force between them. Well, let's go look back at these two diagrams. What forces are acting on them? Now in the 4 kilogram block, you actually have that applied force of 9 newtons. And then of course you have a force of the small one pushing back on the big one. So let's call that our contact force. It's just an action-reaction pair for Newton's third law. Okay, you're pushing on the big block, and then the big block pushes on the small block. Right? And then, due to Newton's third law, the small block pushes back on the big block. So what we're trying to find is the magnitude of that action-reaction pair, which we've called the contact force in this question, Fc. Now to solve for Fc, I could use this diagram or I could use this diagram. Doesn't matter which one you use, but again, we like to solve problems the easiest way possible to make our life easier. This one would be easier. Why? Because there's only one force acting on it. Right? This has another force acting on it. It's another term in our equation that we'll have to consider. So let's just look at this one. Now, if you look at that one, sum of all forces equals mass times acceleration. That mass is always the mass with the free body diagram that you're applying the equation for. Now the only force is our contact force, so Fc, and that's going to equal the mass, which is 3, times the acceleration, 1.3, and you get 3.9 newtons. That's it. You're done. Very easy. If you chose this one, is that wrong? No, absolutely not. You're just, again, making your life a little bit more difficult. But let's just do it anyways. You don't have to do it both ways either. Just the one. You're done. I'm just doing it to show you. So the sum of all forces equals ma. Again, that m will be our 4 kilogram because that's what we're applying this equation to. But we have 9 newtons minus Fc, which equals mass times acceleration. Rearranging this equation, you get Fc equals 9 minus ma, 9 newtons minus ma, 9 newtons minus 4 times 1.3 equals 3.9 newtons. There you go. We calculate the magnitude of both, and we're done. Now, sometimes I get students saying, wait, shouldn't they be equal and opposite? And sometimes I get students with their calculators, it's actually 3.8 newtons. Okay, let me address both of those concerns. One, yes, if you punch those in your calculators, it is actually 3.8 newtons. So why are they different? Well, round off error. If you were to go back to our question in part A, 9 divided by 7 isn't exactly 1.3. 9 divided by 7 is 1.285714 repeating. So I rounded off. Now, if you were to keep every single digit, then you would get the exact same values. But we didn't do that. Okay. Next one is, why is 1 not negative? Well, look at what we did. We chose a positive direction for our coordinate system. Now, if you were to write out every single direction, you would see. The problem is right there. Okay? I put a negative in for a force that I was solving for. Why did I do that? Because I already knew the direction. Right? I already knew that it was in the opposite direction of our positive direction in our coordinate system. So I switched the direction and threw a negative in front of it. Right? Because I switched that direction and threw a negative in front of it is the reason why we get a positive value. Right? If I didn't assume its direction and I simply solved, I wrote plus f, let's do this in green, a different color. If I wrote plus, left this in vector form because I don't know its direction, okay, well then what would happen is, well, you would get a negative. So now I'm actually solving for its directional property as well. Okay, but if you already know it, the direction, and you want it to look nice and positive, that's fine. But just know that's why it happened. All right, now for the last question, we're going to use this exact same strategy we did for this question. So what was exactly our strategy? Our strategy was when we're solving for acceleration, we took the whole mass of the system, right, and solved for acceleration. Then, when solving for a contact force, we chose one mass or the other and applied our equations to that free body diagram. And that's how we're going to solve our last question. So our last question looks like this. We have 2 blocks connected by a string passing over a frictionless pulley, as shown on the side. The larger block has a mass of 3.5 kilograms and the smaller block has a mass of 2.3 kilograms. Now, even though we didn't specifically solve this problem in grade 11, our lab on Newton's second law was this exact setup. Okay, so we have kind of addressed it, and now we're going to dig deeper. So here we have our table, one mass and a pulley going over down to the other mass. I'm just going to write this as big M and this one as small m. Okay, then we have to calculate the acceleration of the blocks. Let's just draw as much information on this as possible. So this has, well, it's got gravity, mg, it's got a normal force, there's no frictional forces yet. Here we have a tension force in this direction, and here we have a tension force in this direction. Here we have a gravitational force in this direction, small mg. All right, those are all of our forces. Now this tension and this tension are the same, right? Because this is the same rope. It's passing over a frictionless pulley. That's important, right? Obviously, if I pinched the rope and held it and applied other forces on the rope, well, then you could have those tensions as different. But right now, with a frictionless pulley, the only thing that pulley is doing is changing the direction of the force, not the magnitude of the force. Okay? So, what we can actually do is draw a free body diagram. Now, we technically already drew it, so let's just assume that's one and that's the other. But we need a coordinate system. So for this one, acceleration is in this direction, so let's use this as positive x. But in this one, acceleration is this direction. So let's choose downwards at positive x. Why did the acceleration change direction? Because of the pulley, right? The pulley is actually rotating our coordinate system. Okay, it's changing the direction of the force, right? And so on. We can have a positive y. We're not really going to need our y component in this question, but I can just throw it in there just so you can see. Okay. Now to find acceleration, what we're going to do is consider this as an entire system, like this. Okay. And in this system, we have two types of forces. We have internal forces and external forces. Okay. This tension is an internal force. Okay. It's literally if I were to take myself and start going like this and pulling on myself, really, if I pull on myself, is that going to cause me to accelerate? No. These are internal forces. Okay. So we actually do not need to consider tension at all. What about these two? Well, these two are external forces, but since we're only going to look at Newton's second law in the direction of acceleration, which is along x, these are along y, I'm just going to ignore them for now because we're not going to do y. And I'm going to go back and erase y. Okay. So what is an external force then? Gravity. Gravity is actually the only external force acting on this system in our x direction. So if I'm to apply Newton's second law, the sum of all forces equals ma. Well, which m? Remember in the last question we used 70 kilograms, which was the sum of both. So we're going to do m plus m times a. Well, what forces are acting? Well, it's just this one. Remember, these are internal forces. If you want to, you can even write down the internal forces. Right? But all you would be doing is writing mg plus ft minus ft. They cancel. That's why they're internal forces. Gone. Okay, which equals m plus m times a. And then you can solve for a. A equals mg divided by m plus m. And then we can plug in what are our values. So small m was 2.3 times 9.81 divided by the sum of both, 2.3 plus 3.5, just 3.9. So you have 3.9 meters per second squared. Now there is another way you can solve this problem if you don't like considering the entire system. You can consider the blocks separately. It's a lot more work, and so I don't know why you'd want to give yourself that work, but I will show it to you. Okay, just this one time so that you've seen it. Let's consider them separately. So let's do sum of all forces equals big MA, and the sum of all forces equals small ma. So we're going to apply Newton's second law to our large mass and then again to our small mass. To our large mass, the only force acting on it is tension in our x direction, which equals ma. For our small mass, right, we have gravity, which is in our positive direction, mg, and then minus tension, which equals ma. So what do we have here? We have two equations with two unknowns, a and ft. But ft equals ma, so I'm going to take that and sub it in here. So we'll have mg minus big Ma equals small ma. Now you just need to rearrange the equation, right? Bring all your acceleration terms to one side, factor, isolate, and so on. So we're going to have ma plus small ma equals small mg. Factor out the a, which is big M plus little m equals mg, and divide. So a equals mg over m plus m. And there, same equation we got here. A lot more work, right? But you came to the same result. If you were doing this question on a test, which method would I want you to use? I don't care. Right? You can use whichever method you're comfortable with. But it's good to understand how both work because, again, right now this is a fairly simple problem. We're going to make this more complicated by adding friction, and also in your homework question, I actually put this one on a ramp, right? And we can add friction to the ramp, okay? Lots of fun. Okay, this way is going to make things a little better, and doing it this way helps you to better see the big picture. And so I prefer it this way. This way is more work, more algebra, but hey, I love algebra, so that way is fun too. Now, we are going to have to come do this anyways because part B says calculate the magnitude of the tension. So this is like our previous one. You're going to have to pick one of these blocks and solve it. Again, I would pick the big blocks because if you look at the equation, let me just erase this part. If you look at these two equations, this one has that extra term in it. So why give yourself the extra work? If you do this equation, you just have tension equals big M times A, where big M is, what is it again? 3.5, and A is 3.9. So 3.5 times, we have 13.6. But we should have only two significant digits, so 14. There you go. And that's it for that question. And now there are some challenge questions, like I told you in your homework. It's question number 10, I believe. Okay? And also the challenge question I put on this sheet is also quite interesting and fun to do. So try those. In the next lesson, we're going to go over friction and frictional forces. And I'll also quickly show you how to start question number 10 if you were having troubles with it. But definitely try it first. Okay? See you next time.